All right, welcome to The Explainer. Today, we're going to pull back the curtain on maybe the most important piece of software on your computer. You know, the one doing all the heavy lifting behind the scenes. We're talking about the operating system.
I mean, think about it. It feels instant, right? You double-click an icon and boom, your app opens. But what's really going on there? Well, that one little action kicks off this incredible, super fast chain reaction, and it's all being managed by the very thing we're going to break down today.
So, to really get what's happening, we've got to meet the mastermind of the whole operation.
Okay, so what even is an operating system? At its core, you can think of it as a resource manager. Or, you know what? A better analogy is a super efficient CEO for your computer. Its entire job is to manage all the company's assets. We're talking about the CPU's time, the system's memory, all your files, and literally every single thing plugged into it. Your keyboard, your mouse, your printer, you name it. It's the ultimate go-between.
All right, so job number one, and this is probably the most obvious one, is just juggling all the programs you're running. Seriously, right now, as you're listening, your computer is probably running dozens of apps and little background tasks all at the same time. And here's a really important distinction we need to make. When your web browser is just sitting there as an icon, we call that a program. It's basically just a passive file on your desk. But the second you double-click it, the OS breathes life into it. It becomes an active process that needs stuff. It needs resources. I love this analogy. A program is the recipe, but a process is you actually in the kitchen cooking.
So how does your OS make it look like you're a multitasking genius? Well, because it's a multitasking genius itself. It uses this technique called multiprogramming, which just means it keeps a bunch of processes loaded up in memory all at once. The whole point is to make sure the CPU, the brain, always has something to work on. So if one process is just sitting there waiting for a file to download, the OS doesn't wait around. It instantly switches the CPU over to another process. Not a millisecond is wasted.
Okay, but how does it actually do all that switching back and forth? It uses this really clever trick called an interrupt. Just think of it like a doorbell for the CPU. When a piece of hardware, say your mouse, needs attention, it rings the bell. The CPU immediately stops what it's doing, and this special part of the OS called the interrupt handler comes and answers the door. It takes care of the request, like moving the cursor on your screen, and then tells the CPU, all right, you can go back to what you were doing. And this happens thousands, maybe millions of times a second. It's wild. Okay, next up, the OS also has to be a master organizer. It's kind of like a brilliant librarian for every single piece of data and every nook and cranny of your computer's memory. Now, to stop total chaos from breaking out, the OS does something really smart. It gives each process its own private, little simplified map of the computer's memory. This is what we call a logical address space. As far as the process is concerned, it has all the memory in the world to itself, starting right at address 0. But that's not the reality. In the real world, the OS has actually stashed it somewhere totally different in what we call the physical address space. This separation is absolutely crucial. It's what stops your web browser from accidentally messing with your music player's data. So how does that translation from the fake address to the real address actually happen? Well, the magic is done by a special piece of hardware called the Memory Management Unit, or MMU for short. What it does is it takes the page number from the program's made-up logical address, then it looks up that page in a master list, a page table that the OS keeps. It finds the real location, the frame number, and creates the actual physical address. It's this lightning-fast lookup that makes the whole system work, and it's what guarantees your programs stay in their own lanes. The OS is also in charge of all your long-term storage. And it does this by creating this really elegant and simple idea that we all know and use every single day: the file. I mean, underneath it all, a hard drive is just this giant, messy collection of data blocks. But the OS hides all that complexity and just gives us this simple, organized concept of a file. And yeah, the OS is responsible for the entire life of every single one of your files. It handles creating them, deleting them, it figures out how to map your Word document onto all those physical blocks on the drive, and maybe most importantly, it acts as the gatekeeper. It enforces the rules about who's allowed to read a file, who can write to it, and who can even open it in the first place. So you've got all these processes running, all these files being opened and closed. The OS has another super important job. It has to be the system's bodyguard. It's got to be strict but fair, protecting the whole system from programs that misbehave, and just as important, protecting programs from each other. How does it do that? Well, this protection comes from something called dual mode operation. See, all your applications, your browser, your games, whatever, they all run in this limited, restricted area called user mode. They can't just go and talk directly to the hardware. But the operating system, it runs in the super powerful, privileged kernel mode. And from there, it has total unlimited access to everything.
So what happens if an app needs to do something that is privileged, like saving a file? It can't just do it on its own. Instead, it has to formally ask the OS for help. It does this by making what's called a system call. You can picture it like a program in user mode politely raising its hand and saying, "Excuse me, Mr. Kernel, could you do me a favor and save this file?" The OS then takes over, does the job for it in kernel mode, and hands back the result. It's a very controlled process.
Let's just take a step back for a second. All of this complexity, I mean, the process juggling, the memory translation, all these system calls, this is what makes building an operating system one of the hardest jobs in software engineering. It really brings to mind this famous bit of wisdom among programmers called Kernighan's Law. The point is, building these things is incredibly difficult, which makes it all the more impressive that they work so reliably for us, day in and day out.
And look, these core ideas we've been talking about, managing resources, juggling tasks, and providing protection, they aren't just for one type of computer. They are the universal foundation for literally every modern operating system you have ever touched.
There's this concept called virtualization that really takes all these ideas and cranks them up to 11. You have a special kind of OS, a virtual machine manager, that can run multiple guest operating systems all on one physical computer. The big difference here is the level of isolation. Instead of just protecting one process from another, the VMM protects an entire operating system from another. It's the ultimate resource manager, juggling the hardware for everyone and keeping each OS completely contained in its own safe little sandbox.
And these fundamental ideas, they now power every single corner of our digital lives. The core OS principles are exactly the same, whether we're talking about the gigantic data centers that run the cloud or a tiny, specialized, real-time OS inside a car's engine that has to be perfect because it absolutely positively cannot be late if it needs to fire the airbags.
And yeah, that supercomputer you carry around in your pocket, it runs an incredibly sophisticated operating system. Android, for instance, is built right on top of the Linux kernel. And iOS shares a lot of its core DNA with its bigger cousin, macOS. They all use the exact same principles we've been talking about: processes, memory management, and system protection.
So the next time you double-click an icon, just pause for a second and appreciate everything that's happening under the hood. It's not magic. It's the brilliant, incredibly complex, and almost totally invisible work of your operating system. And as our devices start to fade more and more into the background of our lives, the next great challenge for these unseen managers is, well, it's to run our entire world, completely and totally seamlessly.